there are many ways of application of the multi-point constraints. We are going to study 3 of them because they are the most broadly specified methods that are used. The first method is a master-slave relation. Yeah, as it sounds, it's very easy. Okay, what we do is that it just sounds like a master, as intuitive as it can be. You have a certain relation which is defined in a format that we did before. So say for example ui is equal to half of uk. So you can write this as ui minus half uk is equal to 0 is your multi-point constraint condition. And when you want to now modify your displacement vector to get to the modified equilibrium equation, then one of these nodes have to be defined as a master, the other one has to be defined as a slave. So if we choose to define I as the master and k as the slave, then the change that we make in the displacement vector is that ua, ub, ui, uj, uk, say it's the last one. If this is u, then the modified u can only be such that the slave node disappears from the modified equation. That means if the slave node is k, then we will have ui, uj, and the uk will go away, will be gone. The relation of uk will also start showing up in terms of ui. And I will show you how exactly that happens. But the main principle is that the uk will be replaced by its relation with ui. So 2 times ui is uk, for example. Then the next method, very standard method of application, is the penalty augmentation. It's called the penalty augmentation. But the reason why we're not going into a lot of theory behind all these methods is that you can always find these things very principally in a commercial finite element package user manual. And all the software actually use different terminology, slightly different equations to describe it. So it becomes very difficult also to describe it for a particular case. Yeah, but also my idea is here to give you a basic taste of what it is, how it works. And then for rest of the details, I can always recommend you to some very, very good literature that will help you understand more details of it when you need it. So what you do in the penalty augmentation method is that you add these penalty elements into your stiffness matrix. Okay, so here the changes are happening. After you have done the master-slave arrangement, you will have to change some things in terms of a penalty weightage. So you add fictitious penalty elements. These are added into your system. And these penalty elements come attached with certain kinds of weights. I will also show you in details a bit more as to what exactly does it look like and where is the difference with the other methods. And then a final final method is the Lagrange multiplier. It's quite similar to the penalty augmentation, but in terms of a multiplier as a Lagrange formulation. Like you're already used to the Lagrange multipliers for solving equilibrium equations which are unbalanced. And in this case also, just as the Lagrange multiplier method, a standard one, what you do is that you add an additional unknown. So an additional unknown is adjoined to the equilibrium equation. This adds some complexity, and physically it represents some constraints. Physically represents constraints. Okay, so these are the basic 3 methods of adding multi-point constraints into your problem. Now let's look at let's look at examples of how we do it, so it becomes much more clearer as to what it really means. Now, of course, all these stiffness matrices are going to be very big, so I'm going to try and use the smallest stiffness matrix I can, just so you get an idea of how it's working. Let's start with the first method, which is the master-slave. This is by far the simplest one. Now say suppose we take in the master slave method, we have a equilibrium equation which is written for, I'm going to pick 7 nodes because it's much better to show. So I'm going to pick K1, K11, K12, K12, K22, K23, K23, K33. So this is basically global matrix, as you can clearly identify. So I put together many one-dimensional systems, it seems like, and I got this as a result. Almost done. And of course the rest of the matrix are zeros. And then I have a displacement vector u1, u2, u3, u4, u5, u6 and u7. And for the equilibrium equation, this is equal to forces F1, F2, F3, F4, F5, F6 and F7. Okay, now say suppose we have a multi-point constraint where u2 moves the same as u6. So if I want to write it in the form of a multi-point constraint equation, it's u2 minus u6. And this basically represents nothing but a rigid link, just as the one I showed you before. So if u2 moves a certain direction in a certain with a certain magnitude, u6 will actually follow it. So it just follows. So what happens now is that I have to change this U matrix. Yeah, that has to change because, as I said in the master slave arrangement, the slave has to fall out. And in this case, I am enforcing U to be the master. So what happens is that U1, U2, U3, U4, U5, U6 and U7, which is the original displacement vector, has to be transformed into something that is U1, U2, U3, U4, U5 and U7. So the 6 has fallen out. But I need this matrix, which is again another kind of a transformation matrix, so that I can do this change. So how do I make this change happen? I know that U1 is still there, so nothing changed, and the rest are 1, 2, 3, 4, 5, 6 total. That means it should be a 6 by 6 matrix. So this is what it will look like. The U2 stays because, yeah, U2 is U2. U3 also stays. So I have 1 in the place of U3. U4 also stays. And U5 in the same way also stays. Now there comes U6 is gone, right? That means I must have something in place that can that can compensate for U6. That means U6 is actually equal now to U2. So in this case I can just write U2, put a 1 here and the rest remains 0. And U7 remains U7. So I have nothing but 1 at the end. So this is my transformation matrix. So this is a transformation matrix T, which now has to be applied to K to make it into K dashed and F to make it into F dashed, and I would have my modified matrix. Yeah. So this is just the basic method of how a master slave method for multi-point constraints is applied. Now the next method that we saw was the penalty augmentation. So for the penalty augmentation, it's slightly different. In the case of penalty augmentation, I want to use the same matrix. So actually what I would really like to do is pick up the same slide and I will copy it. And then I can use the same principle here and change some things that I don't need. So for example, I'm going to need a new description of the augmentation approach, but the rest sort of stays the same because I'm using the same MPC condition. And we already know it's a rigid link now, so I don't need to explain that clearly. Okay, so we are going to use the same condition. Now in the penalty augmentation, I said there would be a weight applied. Yeah, and this weight is generally in the form of a artificial stiffness. Okay, so for example, if this is a bar problem, and it's a rigid link that is describing this MPC, then we want to add a certain weight which describes an axial stiffness which is extremely high to connect two nodes. That means you're just making it rigid, very, very, very high or infinite stiffness. So I can also describe this multi-point constraint as a weighting function times stiffness element. So I have that stiffness W, which basically is a K that we are used to. Stiffness element times U2, U6 is equal to no load acting. There's no force at all. So this becomes my equilibrium condition, and this K is very, very high. So how this is going to change is that it's going to add certain elements into the stiffness matrix. So we will add penalty element, and when I said element, I actually meant an element to the stiffness matrix. So instead of writing the whole stiffness matrix, I'm just going to add the penalty terms into the existing stiffness matrix. So I know that I have a stiffness that is related to K2 plus and minus. So that means here I will have plus W, and when it comes to the point of 6, U6, I have to have minus W. So basically I have zeros here. I should write it down to make it much more transparent. Yeah. And in the same way, I will have the other the W with -1 times U2 and plus U6 also have to come in. So you have a minus for U6 in the beginning. So here minus U6, this one, and then 1 with U6. So there, I know that it comes in the 6th row, which is right here. We are at it right now. So it's minus W. And then I will add stiffness to K66, which is plus W. And that becomes my new stiffness matrix. That means I've added 4 terms which are related to a new stiffness element that is added into the system as a penalty. So only the K has changed into K dashed and the rest has remained. Only K transforms into K dashed. Yeah, so we don't get rid of the nodes, etc. Final example is that of a Lagrange multiplier. That is the last method that we will talk about. So the Lagrange multiplier is as I said, it's just going to also have an additional constraint which is added into the system. It's physical constraint. So we want to add a physical constraint to mimic the situation. Okay, so I would like to use the same stiffness matrix, etc. So I'm not going to write it because here no change actually happens inside the stiffness matrix or the displacement vector in the first step, but actually the change happens in the force vector. So you see, this is the third method and already a third location where this constraint or this new additional term is added. And in this case, the K remains the same, the U remains the same, but the F will change. So if we had F1, F2, F3, F4, F5, F6 and F7 as your forces, then, and the same MPC was applied, that means U2 minus U6 is equal to 0 was still applied here, then we would actually add, remove, let's say add, remove to make a balance of the forces. So we would reduce a certain term lambda or certain Lagrange multiplier lambda from F2, and we would add the same Lagrange multiplier to F6 because the relation has to do with U2 and U6. So those are the nodes where I need to have an appropriate constraint force to mimic the situation. And in order to actually solve this problem, yeah, I need to make a change to something on the left hand side, the KU side. So what I do is that I add another extra row into the displacement vector as this multiplier term lambda, such that I still maintain the equilibrium conditions. So for example, if I had the whole K matrix, which I'm not going to write down, but I had the entire K matrix, which had the first 6 by 6, 7 by 7, this setup, then I would like to get the displacement vector to change in a way that I had u1, u2, u3, u4, u5, u6, u7 and another term which is the Lagrange multiplier lambda. So if I want to keep this under equilibrium such that I still have on the right side f1, f2, f3, f4, f5, f6 and f7, then I need to add an extra row column over here in the end so that I can multiply with lambda to get the same result. That means I'm going to add something to u2. Yeah, going to multiply that with u2. So there would be a lambda here plus 1 because I'm doing f2 plus lambda. Sorry, f2 minus lambda. So I will have a lambda on this side which goes to the opposite side becomes minus. And in the same way, when it comes to u6, 4, 5, u6, we would have a minus 1 because here it would be minus 1. When it goes to the opposite side, it would become f6 plus lambda. And you would have a 0 in the end for the lambda itself. However, this is now incomplete because you had a 6 by 6, you add another row, so it became a 6 by 7. Sorry, you had a 7 by 7 and it became a 7 by 8. So you have 8 columns now. Here you have a 8 by 1, but here you still have a 7 by 1. That means to make it in equilibrium, to make it more consistent, we would have to add another row, which is basically the same as the column that we added to keep consistency. Then we would have 0, 1, 0, 0, 0, minus 1, 0, 0. So once we add this, we would also have to add another column, another row in the force vector. So then our final matrix would be a 8 by 8 multiplied by 8 by 1 multiplied by a 8 by 1 new vector. So that is the method of the Lagrange multiplier. So these are just different methods. I want to give you a flavor of how it works. We are not going to work out examples with this, but when you use these properties or these methods in the program, you will know exactly what you are meddling with and to make sure that you have done it correctly so the system is still under equilibrium in case you don't find convergence.